Good afternoon, everyone. Today I'm introducing our work on PAIC, Parallelised Attentive Image Captioning, presented by Ziwei from the University of Queensland, co-authored with Associate Professor Huang and Yadan Luo. So in recent years, the advances in computer vision field are growing rapidly. The promising results from tasks such as image recognition, object detection, and image segmentation push this area to a new level thanks to the fast-growing convolutional neural networks. In the meanwhile, natural language processing area is also benefited by deep neural networks. The neural network-based machine translation, speech recognition, question answering are also attracting much attention. However, these two directions are traditionally separated. Our research is focused on how to bridge these two directions into a single framework efficiently. So first, let's talk about image captioning briefly. We take an image and we describe it with a sentence, so-called image captioning. It is a basic application to bridge the gap between computer vision and natural language processing. Here is a simple example. Let's look at the image on the left. It shows several objects, such as the cat, laptop, keyboard. Then we need to describe it in a fluent, natural, and informative sentence. The captioning model can generate such a sentence given the image. A cat lying next to a keyboard on the laptop computer. So, why? Why is it so important? The automated captioning can let the robotics have the ability to talk, can help the visually impaired people to see the world better, and allow the autonomous cars to report the road conditions automatically. Next, how? How can we achieve this? Most image captioning models consist of two main parts, the image encoder and the language decoder. The input is a raw image, and the final output is a sentence. The encoder network maps raw inputs to feature representations, and the decoder network to take this feature representation as the input, process it to make its decision, and produce an output. This is called an encoder-decoder network. Mathematically, the model learns the probability distribution over the words in our vocabulary given the previous word and the image. For the encoder, it inputs a raw image, goes through several convolutional and pooling layers to extract feature vectors. The convolutional neural networks use filters to do convolutions on the image in order to get the feature maps. The filter slides through the whole image to get the local features. The convolutions essentially element-wise matrix multiplication between filter and image. Then we're going through subsampling convolutions to preserve salient features. Finally, we concatenate all the convolutional features fully connected layers to our desired dimension. The modern deep architectures, such as the AnticNet, VGG, ResNet, are all built on this basic framework. Next, let's go to look at the decoder. The decoder aims to decode the image feature vector to the sentence. In practice, since we only know the image and no sentence information is given, so we decode this one word by one word recurrently. And here we use the previous predict word as the input of next step. Finally, we write down the entire sentence. Humans don't start their thinking from scratch every second. As you listen to this presentation, you understand each word based on your understanding of previous words. You don't throw everything away and start thinking from scratch again. The recurrent neural networks exactly address this issue. They are networks with loops in them, allowing information to persist. LSTM are a special kind of recurrent neural nets, which are capable of learning long-term dependencies. However, it still has some drawbacks. To learn a recurrent neural network, the standard process is utilizing the backpropagation through time (BPTT) strategy. Consequently, the RNN-based methods often suffer from the issues of the gradient vanishing problem, especially in long-term dependencies learning. To this end, a recent search of interest in finding efficient alternatives for sequence modeling has been widely discussed. Recent work enhances the object recognition and enriches the interpretation of the critical details by incorporating different learning models, such as object detection, semantic attributes, attention, and reinforcement learning. While some encouraging performance are reported, training RNN-based decoder is still time-consuming and incapable of parallel computing due to the limitation of BPTT. To alleviate the bottleneck of time-consuming RNN training, we introduce an efficient parallelized attentive image captioning model, PAIC, that leverages the pure attention mechanism as a decoder without RNNs. This paper proposes a novel framework to explore the pure attention mechanism in image captioning, which allows the model to adaptively highlight salient parts of textual and visual context. The efficient multi-head attention mechanism empowers fast parallel training benefits. At the same time, long-term dependencies are easier to be learned during training. Finally, quantitative and qualitative analysis conducted on the challenging MS-CoCo dataset illustrate the efficiency and effectiveness of PAIC. Here, let's look at the overview of the proposed framework. The visual regions are firstly extracted from the original image, which is further self-attended via a visual encoder. For language decoding, the self-attention module firstly finds a relevant textual context, and the spatial attention module shifts its focus on most salient visual regions subsequently. The next one is predicted based on the output from the spatial attention. All the time steps separated by the dot lines are able to train in parallel efficiently, so-called parallelized. Now, let's look into the attention mechanism in detail. To enable the parallelized model training, we build the PAIC based on multi-head attention, as shown on the left. The attention model maps the queries and a set of contextual key value pairs to an output. The queries are firstly projected into mini queries. Keys and values can be fed to each attention head. The underlying reason is that all the attention heads can capture different implicit alignments in parallel. Then let's look at the spatial attention on the right. In our model, the region visual features are extracted by fast RCNN. The spatial attention model efficiently learns the weights over image regions given current word sequence representation, and guides the language decoder to focus on the most salient regions to predict next word. Spatial attention illustrated on the right. It is an alignment mechanism to give the language decoder evidence to decide where are the most relevant regions at the current position. The inputs are the current language feature and the self-attended region features, and the output is a context vector. So we have two types of attention. Let's go back to the overview of the PAIC framework. As I mentioned, our model is based on pure attention mechanism. The multi-head attention is used in three different ways. First is a visual encoder. The fast RCN features are firstly forwarded to a self-attention mechanism to calculate the relevance between different object regions in order to obtain the final visual representation. The second is language self-attention. It reasons the relevance of the previous and current words. In this way, the representation can capture all the history information. And third is the spatial attention. This module can find related visual regions to refine the self-attended word representations with visual information. Okay, so we present some of the examples caption generated by our proposed PAIC model. We can see the PAIC model generates a sentence in an accurate and visually grounded manner. Let's look at the third image. For example, on this image, it can precisely identify the brown and white color of the dog, as well as the red fire hydrant next to it. You can find more details in our paper. We also studied the training efficiency of our model. As shown in the training curve, the green line on the top is the proposed PAIC showing faster climbing and higher peak performance in both CIDR and meter metrics. For a CIDR curve on the left, we can observe that all the LSTM-based state-of-the-art attention models, such as up-down attention, SAST attention, needs around 15,000 iterations to climb up to CIDR 1.0, while the PAIC only taking around 5,000 training steps. It's much faster. Finally, the performance table shows our model can train a model with state-of-the-art performance but much faster. Here we illustrate some observations. For example, CIDR is very good. It indicates that our model have more matched and meaningful n-gram based on TF-IDF similarity between the candidate and the reference sentences. Then let's look at the blue score in the first two columns. You can see a good blue 3 and 4 indicates that our model have more 3 and 4 gram matching phrases, showing that our captions are more reasonable and they are both widely used metrics in captioning model. I mean the blue and CIDR scores. So last, let's look at the frequent questions. The first question is, can this model generalize to other applications? Well, sure, yes. We can use the image captioning technique to quickly index visual content into semantics for efficient content search. Or for the medical images, such as the X-ray images, the captioning model may help to automatically output prescription diagnosis. Also for the self-driving car scenario, it can report recurrent status telling us what's going on the road. The second question, how about the scalability of the proposed model? Is it fast? Well, the training do take some time, yeah, but testing is very fast in milliseconds. The focus of this work is to accelerate the time-consuming training time while maintaining the testing efficiency and performance. In addition, with the rapid development of tensor processor units, the TPUs, and also the GPUs, it can be even faster. The last question, why do we choose multi-headed structure? What's the benefits? Well, first, it is efficient. All the heads can compute all at the same time. It is faster than going through multiple layers one by one. Also, going through multiple layers can easily cause gradient vanishing issue, but in our model, going through concurrent attention heads can alleviate this issue. Second, it is effective. The different heads are learned with different initialization, and it can capture different aspects of the features. It works similar to the filter in the convolutional neural networks. So that's why we choose a multi-head structure. We use it in 3 ways in our model. Thanks for your attention. Thank you.